what we need in synchrotron, we have to have source of the charged particles, and then we need to accelerate them. And in order to get the radiation, we have to deviate charged particles that are being accelerated, and these particles moving at speeds which are close to the speed of light, and electric fields are used to accelerate these charged particles, whereas the magnetic fields, which can be in the form of bending magnets, Wiggler, and andulators to keep them moving in some closed path. So from the physics, we know that when a charged particle is deviated from its straight path, it emits radiation, and the intensity of the radiation that we get depends on the number of electrons that are deviated from the straight path, and the energy depends on the strength of the magnetic field that we use, and as well as the energy of the moving electrons as well. So until we get the radiation, that depends on the type of the source we are choosing, bending magnet, Wiggler, or undulator. So these radiation, which are varying in energy, when they interact with matter, a different phenomenon can happen. For example, they can be absorbed, diffracted, reflected, and scattered, and depending on the energy of the incident radiation and the nature of the matter with which they are interacting. So I will talk about what happens when the radiation are in the form of X-rays and they are absorbed by the material or the matter. So basically, two phenomena could happen: that the incident X-ray can extract the electron from the core shell of the matter, of the atoms in fact, and depending on the energy, it can ionize the atom as well. So this electron, which is now moved to some higher states, gives rise to a number of emissions that are because of the higher electrons moving to fill the lower unoccupied orbital. So we have X-ray absorption spectroscopy, which is essentially that we have the incident beam, which is incident on a sample, and then we have a reference sample, so that we can compare the reference signal with different samples, so that we can have an idea of the contribution of the different species that are present within the sample. And comparing with the reference sample, we can have an idea of which type of the species is present inside the sample, and these ratios can give an idea which species is present over here. And that's it, we got it. What we need from the X-ray absorption spectroscopy, but the people from the beam line, they said that we have to do something more. We can extract some more useful information from this spectrum. So this is the spectrum that looks like when we obtain for a sample. I have copied and pasted from the presentations, this one. This spectrum can be divided into three regions. The dominant and the prominent one is the rising region, which is named as dense, and the region which is lower in energy to the dense is the background pre-edge region, and then we have some oscillations after the Zans in higher energy range. So this absorption, we can see that this peak is corresponds to the specific element that is present within the sample, and these scattering that give information about the we have to do a lot of things to get the final information, and how to do that we have to do a number of steps, and this is possible with a number of softwares. We have used these tools and we can get information about the elemental identification, the chemical states, and we can have an idea of the structure of the particle system that we are analyzing in terms of the every particle sizes, their shapes, distribution of different plant species or elemental species that are present, and we can have an idea of the surface to volume ratio. And with this, I would like to end this talk, and thank you very much. No question. That's very good.
You see why you're almost missing.
Sorry?
Why you're almost missing? As a veteran, you were missing. You were looking for you. Yeah, again.
Oh, I was about to be nice.